need to wait 2 more minutes to start because the recording of the room starts at 5. So let's wait for 2 more minutes. And just a quick update, we have released the specification for assignment 1. And do you have access to it? Everyone has access, right? Okay, good. So do you have access to the playground of assignment 1? Okay, good. And make sure that you are familiar with this thing here because this will also be used for the final exam. So we will be also using something like this for the final exam. And as for the first assignment, is designed to be black box testing, so you won't get access to the target you are testing. So you are only writing test cases here. So that's the thing we are doing here. And if you are a hacker, I think you can try something weird with the playground, like trying to list all the packages we have imported and things like that. And okay, there's the problem with the light again. Okay, so you can try to Google like how to list all the packages with Python and try to escape the sandbox. But I'm kind of confident that this is pretty strong. It won't leak you the source code. But yeah, you can try. So that's about the assignment, and let's start today's content. So today we are going to learn the very first black box testing technique. And black box testing is also known as functional testing. And I swear that I didn't play with the lights. Maybe let me just turn everything off. Okay. So here is today's outline. So first, we are going to have an introduction to functional testing. And then we will learn 2 functional testing techniques, which we will be practicing with assignment 1. First, functional testing is also known as black box testing. And it is called black box because we don't know we treat the target as a black box. We don't know what's happening inside. And what we do for testing is just to prepare the inputs and observe the outputs, but we don't know what's happening inside, and we don't care about what's happening inside. So because we have no access to the internals of the tested target, so it is kind of like we are doing the testing from the customer's point of view. So because customers, they don't care about how is the product implemented, right? And customers, they don't have access to the source code of the product. So it is done from the customer's point of view. And it aims to test the functionality of the software according to some requirements or specifications. So it is also known as specification-based testing. And talking about specification, let's try to make things clearer about requirements and specifications. So normally we use these 2 terms interchangeably, but here let's try to make the definition even clearer. So for requirements, they are the properties that must be met by the final program. So it is kind of like what kind of output would we expect from certain conditions to be generated by the program. That's requirement. And specification is closer, it's like more concrete. It's more about how the program shall meet the properties, or how would we implement the program to meet the requirements. So it's more concrete. And I know that these two definitions are kind of abstract, and let's take a look at an example here. So let's imagine we are trying to build a password login functionality for maybe a web application. So the requirement could be like this. So the user shall set a password to control account access. So this is a typical requirement. And like discussed, specifications are more concrete. They are closer to the implementations. So what we would do for specification is like this. So we may try to specify the length of the password, which is allowed. We may need to specify the pattern of the password. And we may also specify like how should the password be stored. So as you can see, requirement is like the very high level properties, and specification of features. Specification is more like lower level implementation related descriptions. And a more recent example for requirement versus specification is in AI coding. So if you are familiar with Cloud Code, you might know that we are trying to install a lot of skills using Cloud Code. And if you are not using this skill for your coding agent, I would highly recommend you to use this one here. So it is called Superpower. And it was created firstly by some third-party guy like here, and is now integrated in the official market of Cloud Code because it's so powerful. And in this superpower plugin, if you try to brainstorm with the coding agent, it will generate you two sets of plans. The first plan is called the design plan, and the second plan is called the implementation plan. So if you look at the content of these plans, you will notice that, okay, the design plan is very similar to this requirement, and the implementation plan is very similar to the specifications. And here is a link to these agent skills. If you're interested, you can try it out. So this is a more recent example here. And we know that for testing, do we care more about the requirements or do we care more about the specifications? Specifications, right? Because it's called specification-based testing. So we care more about specifications. So the rationale of functional testing is to derive test cases according to the concrete specifications. And when we do this, we need to follow the principles we have learned. And one particular principle that is very useful here for doing functional testing, like we just mentioned in the previous lecture, is petition. And let's learn about why we care about petitioning here. So a short reason is that the input space for a program is infinite. So we cannot exhaustively test all the inputs to find bugs in a program because the input space is infinite. Even for some seemingly very simple programs, the input space is much larger than you could imagine. For example, for this, have you ever seen this in any web page? Yes, right. So it's called a CAPTCHA, which is like a Turing test, quick Turing test, to test if the user accessing the web page is a bot or a real human, right? And the task, the user input is very simple. So you just drag this piece of image to the correct location to make it a full, complete image. And you may think that, okay, the input is very simple, right? It's just like to check whether this one is in place or not. But it is more complicated than this. So actually some advanced captchas, they don't they don't just check whether the final piece of the image is in place or not. They also check the trajectory of dragging the slider here. So because bots or scripts, they just drag the slider at a constant speed. So, but humans, when we physically move the mouse, when we move the mouse, it's not at a constant speed. So the speed may change. So as you can see here, the speed of dragging the slider is also some sort of input. So even for a very simple program like this, they can have many different forms of inputs. So the input space for programs is very large. But not all inputs, however, not all inputs have the same effect, right? Because we know that for certain inputs, we can trigger bugs. But for different inputs, we can have different outputs from the program. So not all inputs have the same effect. And that's why we can do some partitioning to partition the input space and select representatives from the partition, each partition of the input space as test cases. So that's why we need to do partitioning here. And now let's learn some practical techniques for doing this partitioning. And the first is we are going to learn today is boundary value testing. So boundary value testing is based on this assumption. The assumption is that the density of defect is more towards the boundaries inside of the input space. For example, when we write programs, especially if you are trying to do some algorithm tests, lead code, sometimes you need to bother with whether should I use a smaller than or equal to operator, or should I use a smaller operator, right? This can affect the correctness of your program. So this is an example of a boundary. So smaller than or equal to or smaller than. Another boundary is inside the loops. So for example, we may have different termination conditions for different loops. And there could be some minor differences between a while loop and a do-while loop, right? So there are like many different types of boundaries inside the program. And another potential reason for using this, for supporting this assumption is that sometimes, because requirements are normally written in natural language, and natural language is by nature not very precise, and sometimes when developers are writing programs according to these requirements, there might be some confusions. So if there are like a higher chance that a developer may misunderstood certain conditions at the decision boundaries. So that's why we assume that the defects or bugs happens more towards the boundaries. So now let's take a look at an example here to learn the different techniques for designing the test cases. So assume that we have a program that accepts two integers, and x1 and x2. And x1 should be larger than or equal to a, but smaller than or equal to b. And x2 should be larger than or equal to c, and smaller than or equal to d. So if we draw the input space on a 2D plane, it looks like this. So the valid input space is this gray area. So if the input is within this area, then it's a valid input. Otherwise, it's invalid. So how should we design test cases for this example here? So there are basically two different types of assumptions we need to think about when we try to design test cases systematically. The first assumption we need to have is about the single fault assumption. Just now, the program can take two variables, right? So this assumption limits the number of parameters that can take an invalid value. So this means that failures are, this assumption is that failures are not due to simultaneous occurrence of two or more faults, which means that only one parameter can be invalid each time. So both not both parameters can take the invalid value in the previous example. So under this assumption, when we are trying to design a test case, what we do is, because we assume that only one value or only one parameter can take the invalid value. So what we do is we try to select one target parameter and try to make sure that all the other parameters are taking the normal value and allow the controlled variable to take the extreme value. So this is the assumption here. And another assumption we need to talk about before we systematically design different test cases is about strong robustness. But now let's just apply the assumption we just learned and try to introduce the first variant of boundary value testing, which is called normal boundary value testing. So normal means all the input values can only take valid values. So we don't care about invalid ones. So and according to the single fault assumption, we only allow one value to take the extreme value each time. So what are the extreme values for an input if we under the normal assumption is that the minimum allowed value, a slightly larger value than the minimum value, a normal value, the max value within the valid range, and a smaller value which is just a little bit smaller than the max allowed value. So these four are the extreme values we can take, and this is the normal value we can take. So if we follow this normal boundary value testing design, we can get these test cases. So for example, for here, each dot here is actually a test case. So for example, for this test case, because we only allow one value to take, first, the keyword is normal. So we don't allow any value to take invalid values. So everything is within the gray area, right? So you can see all the dots are within the gray area. No dot falls beyond these lines. And for this one here, it takes the smallest allowed value of x1. But can we put a dot here? No, right? Because this breaks the rule that only x1 can take the extreme value. So we have to allow x2 to be normal. So x2 must be somewhere in the middle. And same for this one. This one is, what is the value of x1 here in this example, in this dot? Can you see my cursor? What is the value of here? It's minimum plus for x1, right? And because x1 is taking an extreme value, so x2 must be normal. And it's the same for these all the other dots. So if x2 takes an extreme value, so what is this value here for x2? It is max minus, right? Max minus. So if x2 takes an extreme value, x1 must be normal, like in the middle. So this is normal boundary value testing under the assumption of single fault. And don't forget the last test case, which is here. So we need to have a test case where everything is normal. So that's for boundary value testing. And now let's think about robustness in this example. So just now we talked about normal testing where everything can take only valid values. But what if we allow values to take a value from invalid range? So if we allow values to be invalid, what we get is robust boundary value testing rather than normal boundary value testing. So what we can have is we can extend the values, the set of extreme values. So minus means minimum minus means a value slightly outside the valid range by being smaller than the minimum allowed value. And max plus means a value that is just outside the range by taking a larger value than the maximum allowed value. And in this case, we are introducing 4 more test cases. So this one here is to make x1 invalid by taking the minimum minus. And this one is to make x2 invalid by taking the value of maximum plus. And this is called robust boundary value testing. So normal versus robust is the difference between valid and invalid. So whether do we allow a value, a parameter to take invalid values or not. And now let's think about, let's try to, just now we had the assumption of single fault, which means that only one value can take the extreme value. Now let's try to break that assumption. Let's try to allow both values to take invalid values. So what happens if we remove that assumption? And we still do a normal testing, which means that we don't take invalid range. So let's do a lab poll. Let's try to look at this example here to see which one represents the worst case boundary value testing. So the values should still be valid. So nothing should be invalid. But this time, instead of allowing only one value to take the extreme values, we allow both values to take the extreme or boundary values. So which one do you think represents the worst case boundary value testing by breaking the single fault assumption? That's the results. So actually, most of you got it correctly. The last one is the correct answer here. So just now you can see the difference. So because we only allow one value to take the extreme value, so no dots are placed near the corner, right? So in this case, if we allow both values to take extreme values, then we can we can occupy the corners here. So this is how it looks like if we do a worst case boundary value testing. So we still take values from this value side, but we allow both values to take the extreme values. So this is the illustration. And now let's combine the two concepts together. What about robust worst-case boundary value testing? It means that we remove both assumptions. We allow values to take invalid values. We allow parameters to take invalid values. And we allow more than one parameter to take the extreme values. What will happen in this case? What will it look like? Can you imagine that? So we are placing a dot in all the partitions inside the 2D space, right? So we put a dot inside all the partitions, and we put a dot near every corner here. So this is the robust worst case boundary value testing. So we allow values to be invalid, and we allow more than one values to take extreme values. So now let's think about how many test cases are we going to have if we do each one of them. So for boundary value testing, if we have n variables, we are going to need 4n plus 1 test cases. And we will learn about why this is 4n plus 1 later. And for robust boundary value testing, we need how many? We need 6n plus 1 test cases. So these two are still linear, right? The number of test cases required is growing linearly in accordance to the number of parameters. And for worst case boundary value testing, what is the number of needed values? Because we are allowing more than one value to take the extreme value. So it's like a permutation of the selections between each variable, each parameter, right? The values. We are selecting values from a limited side, like mean minus, mean minimum, minimum plus, and normal, and so on. So we are selecting from a limited set of values, but we are doing permutations across different parameters. So since we are doing permutations, so it is actually the Cartesian product of this value set, because we are selecting a value for each variable, each one of the n here, from these 5 numbers. So each n can take one of the 5, and we are combining them together. So what is the total number here? It is 5 to the power of n test cases. So we need this many test cases for worst case. And for worst case robust, we need 7 to the power of n. And now let's think about, so you may think that, okay, in reality, because the input space is infinite, so why should we add this restriction of only allowing one value to take one parameter to take the extreme value each time? So this is not how it works in the real cases, right? So why do we need this assumption? So it is because normally we have budgets when we do testing. And as you can see, if we add this single fault assumption, we can avoid the very costly Cartesian product. So the number of test cases only grows linearly as the number of parameter grows. So we need to limit the number of test cases we have. So that's why we need to have some assumptions. And now let's try to do a practice for the boundary value testing techniques we just learned. So here, let's assume that we have a program. So this program takes 3 numbers as input, and each of the number is going to be used as a side of a triangle, and therefore, because in order to form the triangle, these integers must be satisfying these conditions. So let's assume that all of them should be larger than 1 and smaller than or equal to 200. And in order for them to form a triangle, they must be satisfying this mathematics constraints, right? And the output of the program is the shape of the triangle here. So if all the sides are the same, then the shape is equilateral. And if only 2 sides are the same, but the third one is not the same, then it's called isosceles. And if none of the sides are the same, then it's scaling. Or if the constraints are not met, it will output not a triangle. So the three numbers cannot form a valid triangle here. And now let's assume that because now let's think about the values for normal boundary value testing. So for normal boundary value testing, we only care about the valid range. We only care about the valid values, right? We don't care about the invalid values. So we don't have a minimum minus or max plus. So can you give me an example, a value for the minimum value here? I think I messed up with the animation just now, but yeah. So what is the minimum value here? 1, yes. And what about an example for minimum plus? So okay, good. You can also use 3 or 4, but as far as it's close to the minimum value, it's okay. What about a normal value? 50, yes, a good choice, but we just put it the middle value to play safe. What about max minus? 109, yes. And max is 200, yes. And we are lucky that all of them share the same value range, so we don't need to have 3 different sets of values. If they take different, if each of the parameter takes a different range, we need 3 different sets for these values, for these boundary values. So now let's continue. Let's try to practice the different testing techniques. So this is how we can design for a normal value for a normal boundary value testing. So what we do is, like we described in one of the previous slides, is that we fix because we have the single fault assumption, which means that only one parameter can take extreme value, right? So in this case, we need to fix the value of 2 parameters and let the third one to try out all the 5 different values. So in this case, what we can do first is that we can fix the values of A and B to be normal and try to allow C to take different values to go through all the values to try to create test cases. And this is the first batch of test cases created for normal boundary value testing. And we can do the same thing for A and B. So if we want to test B, we can fix the values of A and C and allow B to try out all the 5 values. And if we want to test A, we can fix the values of B and C and try out different values for A. In this case, we can build a table for all the different test cases. And you can see that because we create 5 test cases each time, right? And we do this for 3 times because we have 3 different variables. And we just learned that there should be 4n plus 1, which is 13 test cases. But now we have 5 times 3, 15 test cases. Why? Why do you think it is like this? So why do we have 2 more test cases? It should be 13, right? And it is known as 4n plus 1, but why? Oh, yes, that's the correct one. We have the same test cases, which duplicates for 3 times. So because each time we allow 2 other parameters to take the normal value and rotate the value of the 3rd parameter. And if the 3rd parameter takes the normal value, then we are creating the normal case 2 more times than we need. So that's why we have 2 more test cases. And that is why in the table we have 15, but actually we only need 13. And here, and this can also help us answer why this is 4n plus 1. It's because we are fixing the value of all the other parameters and rotate the value of 1 parameter each time for these 4 values, right? For these 4 values. And we need to do this for n times because we have n parameters. We need to allow each parameter to do this rotation, value rotation. So that's why this is 4n. And because we are not taking care of the case where everything is normal, so that is the 1 here. So that is why this formula is calculated as 4n plus 1. And now, can you quickly tell me what is the number of the worst case boundary value testing here, which means that we allow values to be invalid, but we still have the single fault assumption. What is the number? What is the formula here? Yes, 6n plus 1. So because we have 2 more values in the rotation, so we have mean minus and we have max plus. So that's why the formula is 6n plus 1. So this is all about boundary value testing. And now let's try to learn equivalence class testing. So because now we try to, so when we are designing test cases, we try to design them systematically. And by systematic, what we mean is that we are trying to make the test suite as complete as possible. Although we cannot, because the input space is infinite, we cannot try out every values. We cannot try out every combinations, but we still want a sense of completeness. So that's why we need to do things systematically. We need to design, follow some rules. And we also want to avoid redundancy here. So this redundancy here is not a conflict with the 6 principles we have learned. In the 6 principles of testing, we learned that we need some redundancy, right? But in that scenario, in that context, redundancy refers to we are trying to design test cases from different angles rather than designing duplicate test cases. And just now we saw some duplicated test cases, right? So we also want to reduce redundancy. So these are the 2 things we need to bear in mind when we design test cases. And this also guides the design of the equivalence class testing. And in equivalence class testing, we echo the 2 deciding factors of boundary value testing. So in boundary value testing, we have 4 variants, right? We have normal boundary value testing, worst case boundary value testing, which deals with whether parameters can be invalid or not. And we have the single fault assumption turning on and off, which gives us 2 more variants, which is about whether do we allow 2 or more values to take extreme values or not, right? And here we also have similar deciding factors when we try to think about equivalence class testing. So the first deciding factor is robustness, is whether parameters can be invalid or not. And the second one is whether do we allow multiple values to take extreme values or not. And here is a small example of a small motivating example for us to do equivalence class testing. Remember, in the triangle program, all these test cases, although they are different in values, maybe some of them are taking the extreme values, maybe some of them are not taking the extreme values, but they are essentially the same from the program's point of view. Why? Because all of them will trigger the program to output equilateral, right? Equilateral, right? So that's why they are triggering the same program behavior. They are triggering the same output. So what we can do is, instead of treating all 3 as different individual test cases, we can somehow group them together and use only 1 test case to represent this group. And the equivalence class testing is all about how do we design the classification or grouping of the inputs. And before we jump into the details of equivalence class testing, let's have a 10 minutes break. And I'll see you at 4:56.
We've always playing that we wanted precise for both sides.
It depends on the specification.
If it doesn't have the like, if we don't have the single size, is there anything gonna be changed within the?
Oh, the minimum value or maximum value. It depends on whether it depends on the type of the variable. If the variable is an integer, still we can still have this it's a small universe.
So we don't care if it's within the boundary, we care that it's the boundary value.
Yes, for normal worst case, we care about whether it's within the boundary or not, because we need to care about the validity of the variables. But if but for robustness we don't care. So yeah.
So for example, the normal one, if we want it to be greater than.
Oh yeah, for normal one we don't care. Normal one, because we need to make sure that it's somewhere inside this normal range.
That's it called. It all should be valid.
But just don't near the boundary. Don't make them near the boundary.
Whether it's normal one, it just depends on whether it's all valid.
Normal means valid and far from the boundary.
And the robust one means that we had someone other than.
Yeah, yeah. Sorry. Normal here, if you are talking about not the value but the name inside the name, normal or worst case means normal or robust means we care about whether it's
one error.
No, worst case cares about whether it's one value or not. Normal and robust means whether the parameters can be invalid or not. So if it's a normal testing, then all values must be valid. If it is a robust, then then we can try invalid values.
Just around the
around the boundary. But for worst case, it's about whether do we turn on of the
body error.
Yes. And we will apply this to normal versus robust and the single fault assumption in the testing. Did you try this?
Yeah, I can do the test. Can you see the source code because I tried that there.
Yeah, you can try this.
It's building on the plugin phase, right?
Yeah, it's hosted on Firefox.
Okay,
good.
it's probably fine.
Okay, good.
Thanks.
Yeah, no worries. Okay, so let's continue. So just now we stopped at this point. So we observed that we can see some of the test cases, although they are not exactly the same, but they can be grouped together because they are triggering the same program behaviors. Like, for example, in this case, all these three test cases are triggering the program to output equilateral, right? So this means that they are they are triggering the same program behaviors. So we can just use one of them to do the testing. And how do we identify the different classes, equivalence classes, is the problem here. And in early days, so most of the standard textbooks, they discuss the equivalence classes based on the validity of the inputs. So it's quite natural, right? The inputs can be naturally classified into two classes, like valid and invalid. That's very natural. But and and this traditional equivalence class testing is nearly identical to weak robust equivalence class testing. So we can see the keywords. Robust means values can be invalid, and weak means we only allow one value to take each equivalence class each time. So we don't care about covering all the combinations or permutations of different scenarios, different classes. So we don't care about that. So this is weak robust, and this is how it is done. So given a function f, so because we only have two classes here, valid or invalid, so what we do is we try to test the normal case first. We try to test the value for all variables, and then we test it's like doing the rotation again. So we try to fix the value, all the other variable values to be valid and make one of the variables to be invalid and rotate this step. So this is what we do for traditional equivalence class testing. This is very similar to weak robust. But now let's try to this is something covered in some of the textbooks, but what we are trying to do is we try to systematically learn all the variants, right? And similar to boundary value testing, because we have two buttons here, like turning on and off, so we have four variants. So now let's try to learn the improved ones. And by improving, it actually is not only about the, like the four variants. And this is blocking the. So it is not only about. It is not only about the four variants. It's also about how do we design the classes, because naturally variables can be valid or invalid, but sometimes there could be value intervals for the values, right? And some of the and if the value of a variable falls into different intervals, the program may behave differently. So we can have some intervals. So for example, let's assume that we have a function, and this function takes two input parameters, x1 and x2. And x1 has, and the value range of x1 is between a and b, and the value range of x2 is between e and g. And x1 can take these three intervals, and x2 can take these two intervals. So we have we can generate 5 equivalent classes out for the valid inputs. So this is like we are making the classification of equivalence classes more fine-grained rather than just marking them as invalid or invalid. We can further classify them according to the range intervals within the valid and invalid ranges. So for valid inputs, we can have 5 valid intervals, which are quite natural, which is just the 5 intervals here. And how many invalid intervals do you think we can have in this case? Because valid is very straightforward, right? We just collect all the 5 intervals here to mark them as valid equivalence classes. But what about the equivalence classes for invalid ranges? How many of them can we have? We can have 4. Yeah, I saw some of you got the answer. We can have 4. And these 4 are x1 smaller than a, right? x1 larger than d, x2 smaller than e, and x2 larger than g. So we have 4 equivalence classes for invalid inputs. And now let's go through the 4 different variants for equivalence class testing. So the first one is the weak normal equivalence class testing. Weak means that we use one variable for each valid equivalence class in a test case. So we don't need to care about covering a valid equivalence class with multiple values. Only one is enough. And this follows the single fault assumption. And normal means that we only care about the valid class range. So we only care about the 5 intervals there. And there are different solutions if we design the test cases. And if we put our first test case here, which means that x1 is taking the AB range, x2 is taking the EF equivalence class. So we have covered this. So how do we design the next one? The next one could be designed like this. Since x1 has taken A and B, right? We should, since x1 has taken A and B, x2 has taken E and F. So for the next test case, shall we put it here? No, right? Because we have already covered A and B for x1. And shall we put it here? Also no, right? Because we have already covered E and F for x2. So what we need to do is we put it here. So because we just need one variable to cover one case here. And for the last one, we have to have some redundancy because all the value ranges for x2 has been taken, right? So we have to move, because for x1 we have covered this, for x2 we have covered all equivalence classes. So we just need one more test case to cover the last part. We can either put it here or here, so it doesn't matter. It's a little bit of redundancy here for testing x2, but it's how it is. So this is the design for the weak normal equivalence class testing. And this, as you can see, this depends on the very first choice. So if we choose to put the first dot here, then things would be different, right? We can design the test cases differently. So that's why there are multiple different standard solutions for weak normal equivalence class testing.
So as principle, we do some redundancy test. So can we just add more redundancy tests to double check if there will be no problem with the load function?
Yes. So, but redundancy means trying out different techniques rather than trying the same technique with some duplicate test cases. So here, if we can, because here you can see that we can have multiple solutions where we are only covering like, when you can see the input space is partitioned into so many subspaces, and we are only covering 3 of them here. So if you want to be more, if you want more redundancy, if you want more robustness, we can improve the technique we are using here. So let's try some other variants of equivalence class testing. So, or we try other testing techniques. So now let's move forward. So we can now let's change the keyword weak to strong. So strong means that we are removing the single fault assumption, which means that we allow we need to test different combinations of equivalence classes. So instead of covering each equivalence class once, we need to cover each combination of, or each permutation of the equivalence classes once. So instead of covering the classes themselves, we are trying to cover all the combinations of different valid equivalence classes. And again, this will lead to the Cartesian product, because we are trying to cover all the permutations. And in this case, because we only care about the test cases within the valid range. So everything must be within this rectangle here, right? And we just put one dot inside each of the subspace here to cover the entirety of the combinations of different valid equivalence classes. And do you think there are like alternative solutions, like the weak normal equivalence class testing? No, right? No, because we are covering everything, and there's only one solution here. So this is strong normal equivalence class testing. And now let's we played with the keywords weak and strong, and now let's try to deal with normal and robust. So according to the definition, so for weak equivalence class testing, for weak robust equivalence class testing, what we do is, instead of only allowing the values to take the valid equivalence classes, we allow them to take the invalid classes. And according to this definition, and weak means that we don't need to cover all the combinations of classes. We only need to cover each class once. But we do allow some certain level of redundancy here. And let's do a live poll. Does this image illustrate the weak robust equivalence class testing properly? And for these type of yes or no questions, you can think about using some counterexamples to quickly check, or using a particular test case inside this to check whether it follows the definition or not. So you can think of, at this point, follow the definition here. Some of you have finished. So let's see the results. The answer is no. So let's see why. Both of you have got it correctly. So let's just look at this point here. So this point means that x1 is taking the invalid range. This is allowed. And x2 is, what about x2 for this point? x2 is also invalid. So this breaks the assumption of single failure, single fault. So both x1 and x2 in this point are invalid. So we only allow one value to be invalid. So that's why this is wrong. And the correct one is like this. So only one value is allowed to be invalid each time. So for example, for this one, x2 is invalid, then x1 is valid. For this one, x1 is invalid, but x2 remains valid. So this is one of the correct solutions here. Of course, we can also put this point here, but only one value is allowed to be invalid. And for strong, robust equivalence class testing, it is to test all the permutations of all the equivalence classes, both valid and invalid, and we don't care, and we don't have this restriction of only allowing one equivalence class to take the invalid value. So again, it is a Cartesian product, and it's a Cartesian product of all possible equivalence classes. So you can imagine we are putting one dot inside each subspace, each partition here. So this is a strong, robust equivalence class testing. And now let's come back to the practice. So let's think about the triangle program. So for the triangle program, it is quite special because let's try to remove the length limit for these A, B, and C values. Let's just think about the potential outputs and how we can create equivalence classes according to the potential outputs. So naturally, according to the output of the program, we can have 4 equivalence classes. So the first equivalence class is a set of values for A, B, and C, where the triangle is equilateral, and the second one is isosceles and scaling and not a triangle. So we can naturally form 4 equivalence classes according to the output of the program. And let's ignore the 1 to 200 limit this time. And we can have 4 equivalence classes. And now let's think about the weak normal. How do we design the weak normal equivalence class testing? So weak normal means that everything is normal, right? So what we can do is, so everything is just normal here. So what we can have is we can just have one equivalence class, one test for each class. So this is very special. Let's admit this kind in. And what about strong normal equivalence class testing? So strong means we need to think about, we need to think about covering the permutations between different value ranges, right? But in this example, it's the same because we don't have any sub-intervals, so we don't need to care about the intervals. So in this special case, it is the same as with normal. And if we think about the input domain in a more detailed way, we can see that actually, if we want a triangle to be equilateral, then A, B, and C must be the same. And if we want it to be isosceles, then we can take these three cases. If we want it to be scaling, then we can take this one. If we want it to be not a triangle, we can take this one here. So although we have these sub-scenarios, but we don't really have any sub-intervals for these different cases. So that's why we can just consider this strong normal equivalence class testing the same as weak here in this example. And for weak robust, we allow them to be invalid, which means that we can allow the values, some of the values to be, if we want to talk about robustness, we need to think about the validity of the inputs, and we need to bring back the constraints of the inputs range. So we have to have positive numbers for integers, right? For the size, right? So we need to bring back, because we are talking about robustness here. And previously, if we don't care about the range, everything is valid. So we need to bring back the range here to bring in some validity check for these integers. And therefore, what we can do is, in addition to the weak normal tests, we allow values to be invalid. And this time, because we are doing a weak robust, so we only allow one value to be invalid each time. So what we do is, we can fix B and C and allow A to take the invalid values. And then we fix A and C to allow B to take invalid values. And then we fix A and B to allow C to take invalid values. So this is the weak robust equivalence class testing. So in addition to the weak normal ones, we add some examples for the values to take to be for the values for the variables to take invalid values. So let's keep this assumption here. Let's keep this assumption here because we need to do undo with strong robust equivalence class testing. So comparing to the weak normal ones, what we do is this time we allow more than one value to be invalid, right? So first we try out all the cases where only one value is invalid. And then we try out the cases where two values are invalid. And then we try out the case where all the three values are invalid. But do you think, is this all the test cases we need to add based on the big normal equivalence class testing? Is this all? Yes or no? If you are watching the slides without animation, you can see the answer. But if you are watching it live, you need to think about it. So the answer is no, this is not all. Because why? Because we only care about the cases where the values are smaller than 0, right? We still need to think about values where the values are larger than 200. And there could be combinations of like C1 is like A is smaller than 0, but B is larger than 200. So you can think that there are many permutations here. So this case is only like a corner inside the space. So because we have 3 parameters, you can think the input space is partitioned by a cube. So this test cases only covers a corner of that cube. If we put dots as test cases, this only covers a corner of the cube. And we have many corners. We have like 8 corners for a cube, right? So this is only 1 corner here. And this is one example of this equivalence class testing. And this example is not a very typical one because it doesn't have sub-intervals of for these values. And now let's take a look at a more suitable case for applying equivalence class testing, where values can have sub-intervals. So now let's assume that, let's consider this function here. So this function is known as next date, and it is a function that accepts 3 integer values, month, date, and year, and it returns the date of the next day as output and reads the current date as input. And the conditions for these three variables are quite straightforward, right? We have months, we have some restrictions for months, we have restriction for day, and we have restriction for year. Let's assume that it stops at 2 years ago. So based on these conditions, what are the valid equivalence classes? What are the valid ones? Like, maybe instead of answering what are the valid ones, can you tell me how many valid equivalence classes do we have? It's pretty straightforward, right? We have 3. Because we just have 3 sub-intervals and there's no like things in between, so we have 3. And what are the invalid ones? 6, yes, 6. So we have 6. So each one of them has 2 invalid equivalence classes. And now let's think about different variations of equivalence class testing. So first, big normal. So for big normal equivalence class testing, we only need to care about the valid equivalence classes, right? We only need to care about these 3. And for considering robust cases on not normal equivalence class testing, we need to think about these invalid equivalence classes. So for big normal, we can just do this. So do you think that's all for big normal equivalence class testing? Do you think this is enough? weak normal. Weak means we don't care about the permutations. We just make sure that each equivalent class is covered by at least one test case. And normal means we don't care about the invalid classes. That enough? Actually, yes, it is. It is enough. And for the strong normal, in this case, it's also the same because all of them are we just each one of them has only one subinterval for valid class for valid equivalence class. If we have something in between, like for example, if there's like months smaller than 6 or months larger than 6, then we may have more test cases for strong normal. But in this case, because it's very special, each one of them has only one, each variable has only one valid equivalence class. So the strong and big normal equivalence class testing will give us the same test suite. And now let's think about weak, robust equivalence class testing. So for weak, robust, what we do is we only allow one value to take an invalid value first, to take an invalid, one variable to take an invalid value at the same time. So the first test case is we need to build this weak robust on top of big normal. So it's a superset of the big normal test suite. So let's just reclaim this test case here and think about how to redesign the following test cases. So what we can do is we can apply the invalid equivalence classes one by one. So for M2 here, if we apply this, if we try to cover this equivalence class, what we do is we get a month which is below the valid range, right? We have this one here. And what about the next one? We can make use of this equivalence class, right? What we can get is we can make the months overflow while keeping the day and year valid. And the same goes for all the rest of the test cases. So because this is weak, robust equivalence class testing, each time we only allow one input value to take a value from the invalid equivalence class, and the value of the rest parameters should be from their valid equivalence classes. So this is for weak robust. And what about strong robust? We still have this. So first, what we need to do is we need to reclaim the test cases, right? So because this time it is strong robust, so which means that we allow values to be invalid, and we allow more than one variable to be invalid. So let's just flip the validity of the parameters one at a time. And first we can make use of the months in the invalid equivalence class of months here, and then we can use the equivalence class of day here, and then we can use equivalence class of year here. So we tested that, okay. So this covers the case where one value is invalid. And now what's next? We need to, because this is strong robust equivalence class testing. strong means we can have more than one variable taking invalid value, right? So this time we make one, we can combine the invalid classes. So what we can do is we can combine the months smaller than 1 and days smaller than 1 in invalid equivalent class, and we can get this. And if we combine months and year, if we combine day and year, we can get this. And if we combine months and year, we can get this. And what's next? We combine all three of them, right? If we combine all three of them, we can get this. So, but again, is that all for strong reverse equivalence class testing? No, again, right? Because as you can see from the lines here, some of the equivalence classes are not used at all, right? It's very clear that it's still far from finished. So this, again, is still just a corner. But this is hard to imagine because it's like we have so many restrictions and the input space is partitioned in a very different way. So that's all about the test cases. And before we end today's lecture, let's quickly go through what we have learned. And I will quickly walk through the specifications of assignment 1. So what we have learned today are two families of black box testing techniques. And black box testing is also known as functional testing because we only care about the functions and features of the program. We don't care about the actual implementation. So as far as the program is functioning correctly according to some specifications, we don't care about how it is actually implemented. And can you still remember the difference between requirements and specifications in this context? So requirements are like more high level, right? And specifications are more low level and closer to actual implementations. And for doing black box testing, the key principle here is to partition the input space. And the reason for doing this partitioning is because the input space is infinite for programs. We cannot exhaustively test all the test cases, all the potential scenarios. That's impossible. So that's why we need to partition the input space and select representative values from the input space to build our test cases. And there are two ways of doing this partitioning. The first one is that we can do the partitioning according to some boundary values, right? And the second one is some test cases are naturally having classes. And the most basic class are valid and invalid. And sometimes we also have value intervals, right? So that's the two ways of doing this partitioning. And when we do this partitioning, we also need to have, each one of them has 4 variants. And these 4 variants comes from turning on and off 2 switches. The first switch is whether we are doing normal or robust testing, right? So what does this mean, normal versus robust? Can you still remember? Can you still recall that? What is normal versus robust? Normal versus robust is about whether do we allow the parameters to be invalid or not, right? And the second switch here is the single fault assumption. So what does single fault assumption deal with? So yes. So single fault, if we turn on the single fault assumption, then we only allow one parameter to be invalid at a time. And if we turn off this assumption, if we don't apply this assumption, then we allow more than one input value variables to be invalid. And then because of the two switches, we have 2 to the power of 2, which is 4 variants for each design. And the reason of having this single fault assumption is that because we have limited budget when we do testing, we cannot afford to use Cartesian products to produce test cases in reality. So that's why we need to have single fault assumption sometimes. And that's all for the concepts today. And for the assignment 1, it will cover the 2 techniques we have learned today. And in previous some terms, what we did was we tried to ask students to submit all the robust boundary value testing test cases, which is like Cartesian product, and if the files are very large, because you can write a script to generate the test cases, but the submission file is very large. And now we have changed the format. So instead of like generating a full test suite, what you will need to do is first, given this, so we are trying to simulate a real world black box testing scenario. So you don't have access to the source code, but you can try to interact with the programs here in the playground. And what you need to do is you need to identify you need to apply the concept to identify the key the key values for some key concepts, like for example, what are the boundaries, right? Or maybe what are the equivalence classes, and then you will try to act like a bug hunter and apply the principles or the designs of these test cases to try to find bugs in the program. And each program has 5 bugs, and for each bug you can find, you will earn 0.5 marks. And one thing you need to take note is that there is a hint here, because in our lecture, all the practices and examples, we have one hidden assumption, and that hidden assumption is that all the input variables, they are independent. So they don't they have no dependencies with each other. So that's why we can try to just identify the boundaries purely from the input space. We don't care about the output, right? And for equivalence class is similar. We cared about the output, but we didn't use it that much because we only use it for the triangle program, but we didn't use it for the next state program. So because we just assume that every input is independent, but in reality, the inputs can have dependencies. For example, for the next state, the valid, if we try to make the program more robust, the valid range for a day actually depends on the month, right? So that's in reality, but we simplified the case in our lecture to teach you the core concept here of equivalence class testing. But in the examples, you can see there are some dependencies between these inputs. And there are some decision boundaries or program behaviors that are triggered by the combinations of some interesting values of the input. So each black box target here has one bug that will require you to think about how to combine the different values, how to deal with the dependencies of between the parameters to trigger that bug. So that's all about this. And I hope you can have access to this and you can try to play with it. So you can edit the test cases here. For example, I can duplicate some. And you can see that it's interactive. So you can play with the test cases here before you do the submission. Okay, and that's it for today. And see you tomorrow. And tomorrow we will learn some other black box testing techniques. Thank you.